These will get on Blackboard, by the way. I haven't posted the previous notes yet. I just appended these on. I'll get these up as soon as I get it all worked out. Once it actually is done, it should update automatically and be there like as soon as we do it in class. So you'll have it to look at. But for now, I'll save these for you and upload it. What do you have for that first one? What kind of numbers did you come up with? 3.8. Did I get something different?
3.65.
3.7. 3.65. Okay. Anything else? Nobody got like a million or some crazy number? Okay. All right, so yeah, these are all kind of in the realm of what we want here. Remember the procedure of how we come up with this measurement. We look at what do we know for sure based on the tick marks, and then we make one guess as to one more digit. So for sure we know that this number is going to be between the 3 and the 4. I think we can all agree on that. But as you can see by all the different numbers that we came up with, we could not agree on where exactly that is between 3 and 4. And that's okay. That's what makes it an uncertain digit. We don't know exactly where it is. We guess. So that could be either 3.7, 3.8. 3.65 is probably not a great measurement here because it's an extra amount of precision. So we don't have enough precision to give ourselves an extra decimal place. 3.6 maybe would be okay, but probably 3.7, 3.8 is a better way to go here. What about this next one?
2.50.
2.50? Do we get something different?
2.51.
2.5, 2.51, like that. Okay, so let's look at these. So these are all also right in the same range. It's a little easier to tell with this one. You can see it's kind of right on that line in between the 2 and the 3. So what do we know about this? We know for sure it's bigger than 2, but smaller than 3. And the tick marks tell us that we can be sure about one more digit as well. And then whether or not you see it exactly on that line, that's what you're guessing. Do you think it's on the line? Do you think it's a little bit one way, a little bit the other way? That's what we're trying to figure out. So that means that either 2.50 or 2.51 is a good choice. 2.5, like this, is not precise enough. Because we have that extra level of precision here, we can get that one more decimal place. Remember the difference. When we write 2.50, we're really saying between 2.49 and 2.51. When we write 2.5, we're saying between 2.4 and 2.6. That's a big difference in those two ranges. All right, so then what about C? What do you get for C?
4.10.
4.10. We get something different? Everybody got that? Okay. Yeah, that's what I'd say too. It's right on that first line after the 4. And since we have little divisions in the tenths between each numbers, we can know for sure that it's 4, for sure one more digit, and then we guess that third digit. So how many significant figures in this number?
3.
3. Those are all significant. 2 for sure, 1 is estimated. And in the previous one, and then the top measurement only had 2 significant digits. So once you figure out for a particular tool how many decimal places you can get, it's always the same for that tool. So notice that B and C, you've got the same ruler, the same kind of graduated ruler. So that means that the precision will be the same anytime we use that. And so that's helpful for some of the stuff we use in lab, like thermometers, graduated cylinders. Whenever we make a measurement with that thing, once you've figured out how many decimal places you need, it's always the same with that same piece of equipment. If you look at the, I'm not going to pull it up here, but if you look at the data from lab on Tuesday, you'll notice it's, pretty much okay, but there's definitely some spots where some of the numbers were not taken down to the correct number of decimal places. And you can go back and look at that equipment and see which ones they were. All right. So that's precision measurement. We'll keep practicing this throughout. This actually came from a problem from your book, so please get started with the homework assignment in that first measurement chapter. We're actually skipping chapter 1. Chapter 1 is like a general chapter. There's not a lot of stuff in it. We're starting really with chapter 2, talking about measurements. So you can start in with the homework in that, the assignment on Blackboard. And speaking of measurements, one thing we should note from yesterday, we had this kind of weird tool in lab yesterday. Called a Burette. Remember this thing? It kind of had a little thing at the bottom. It was hanging up in with the A's and B's. This one's unusual because you'll notice it was like 25 down here. And so on. So the scale was reversed. Normally you'd think 0 at the bottom because that's nothing. And then you fill it up and you get more and more. The difference with the Burette is it's meant to dispense liquid, not to accept liquid. So that means that if you run all of the liquid out of a full Burette, you're actually dispensing more than 25 milliliters because of this extra space at the bottom here. So you're only really supposed to go in between where it's marked off. That also means that when you take a measurement on an instrument like this, it sounds weird, but you don't need to really worry about what that measurement is used for, or what that instrument is used for. If you see a scale and you see something on that scale, you can write down the measurement just from there. You don't need to think about what that really means contextually. So what I mean by that is if I have a liquid level, let's say here, and I'm going to say that that liquid level is right there. It seems weird to call that 24 point something milliliters because clearly there's not that much stuff in there. But that level is between the 24 and the 25. Everybody see that? Anything between 24 and 25 must be 24 point something whatever. So we have to write it that way, even though it seems weird. So we would write this measurement as perhaps 24.42. And we still label it in milliliters, even though it's not really a volume measurement. It's like a level measurement. So same with some kind of gauges, things like that. Pressure versus vacuum, which are opposites of each other. Sometimes a gauge will measure pressure, sometimes a gauge will measure vacuum, but you still just read the measurement, whatever it is, based on the scale that you're using. All right. Let's look at metric units, the ones that we will use the most here. So usually this is like a totally new thing for people, but I think in this class we've got several people who grew up outside the US, so you probably are a little more used to the metric system than people who grew up here. But the metric units, the main ones that you need to know that we'll use in lab, we used on Tuesday, and they were part of that pre-lab. So what are some of the metric units that you know?
Centimeter.
Okay, centimeter, so meter, yeah.
Kilogram.
Gram, yeah.
Kilometer.
What else do we have? Liters for volume.
Yeah.
And grams. What else did we use? Degrees C for temperature. So those are metric units. There's a few that you definitely need to know for this class in terms of the conversions. So let's say we're talking about a meter. That symbol is M. Do you have a meter stick here? Yeah. So this is 1 meter. And it can be split up into smaller units, or it can be put together into bigger units. We know that there are 100 centimeters in a meter. We know there are 1,000 millimeters in 1 meter. So the centimeters here are the numbers that you can see, and the millimeters are the tiny little lines. There are 1,000 in a meter. You need to know those two equivalences, and you also need to know that 1 kilometer is 1,000 meters. So 1,000 of these together is a kilometer. The nice thing about the metric system is those prefixes are general and they work for any kind of a unit. So we could say the same thing. We could say that 1 kilogram is 1,000 grams. We could say that there are 1,000 milligrams in 1 gram. We could say there are 100 centigrams in 1 gram. So those prefixes are general. You do need to know those three. They're listed on the objectives on Blackboard. So you need to know what centi means, you need to know what milli means, and you need to know what kilo means. There are other prefixes as well, in between and higher and lower. They're in your book, and if you need them, we'll use them. But those are the only three that you have to know for sure how many of, how to convert back and forth using those. One thing we're going to use this for is, like I said, to convert units. So if something is given in or measured in meters and we want to know what it is in centimeters, we have to be able to do that. So we're going to set up a system for doing that. But the thing I want you to keep in mind while we do that is that it should always make sense. So keep a picture of this meter stick in mind. This is a meter, this distance. The numbers are the centimeters, and the tiny little lines are the millimeters. So if I said, how many centimeters are in 5 meters? And you didn't really know offhand, but we do some calculation, and you type in your calculator, and you come up with 0.5 centimeters. There's 0.5 centimeters in 5 meters. Does that make sense? Is that a reasonable answer? You're shaking your head. Why not?
No, it's too small.
It's too small, because if a centimeter is this big, and a meter is this big, and we want to know how much is in 5 meters, which is a bunch of these, it's not going to be that. It's going to be a bunch, right? A bunch more. So if you keep thinking in those kinds of ways, it'll help keep you from making silly mistakes. It's easy to accidentally push the multiply key on your calculator instead of divide or something like that and come up with some wrong answer. But you should have a little catch in your head before you write that down saying, wait a second, that doesn't really make sense. I know it's got to be some big number. So if I said how many centimeters are in 5 meters, and we'll get to how to do that in a second, but what should the scale of that number be? Like, what? It should be a bigger number, right? Because a centimeter is smaller than a meter. So if we've got 5 of these, we should have a whole bunch of little centimeters. So keep those kinds of things in mind as we talk about some of these conversions. Now I want to show you something called, and you may have used this before, called the factor label method. Does that sound familiar? Has anybody seen this before? Maybe, maybe not. Okay. This is a way to convert from one unit to another by following the units. And this is the way it's explained in the book. Now this might seem a little too simple for something like these metric conversions, which some of you probably have a lot of practice with. But if we do it this way, then when we get to more complicated conversions, we still can use the same process and it will still work and hopefully lead us to the right place. So let's go back with that same question. How many centimeters are in 5 meters? Now, for many of you, you can just look at that and say, oh, well, obviously it's this, because you have practice in that. But if you didn't, you could think about it this way. To do this, we need to know a relationship between centimeters and meters. How many of one is in the other? And there's a couple ways to write that relationship. One way is the way that we already wrote it up here. 100 centimeters equals 1 meter. Another way to write it is to manipulate this a little bit mathematically and say something like 100 centimeters divided by 1 meter equals 1, meaning that those two are the same thing. So you're dividing the same by the same, or flipping that, 1 meter divided by 100 centimeters equals 1. So those are just a couple different ways to write this kind of identity. How we use that in a problem like this is we say, all right, it's saying how many centimeters. So that's what I want at the end. That's my, I don't know what it is, what I want to know. And then 5 meters is what I've been given. So I'm starting with 5 meters. And I want to end up, do some kind of math to end up with a certain number of centimeters. Everybody with me so far? How we do this in this factor label method is by tracking the units, by getting rid of units that we don't want and getting units that we want in their place. So we would say, all right, I have meters here, and I want centimeters. So that means I need to get rid of meters and get centimeters. The way we do that is by introducing a factor, a multiplication factor, that can cancel that unit of meters and replace it with a unit of centimeters. Another way that sometimes we'll write this is we'll divide this first number by 1, just to show that it's on the top of the fraction, but same thing. Because there's an m on top and an m on the bottom, those actually cancel from each other, because something divided by itself is 1. So that means if we can fill in this fraction with a relationship between centimeters and meters, we can complete this expression. We know the relationship between centimeters and meters from what we wrote down up here. There are 100 centimeters in 1 meter. And then to complete this expression, we multiply everything on the top and divide everything on the bottom. Now right here, all we have is 5 and 100 on the top. So 5 times 100 is 500. The bottom is all ones, so dividing by 1 is the same. So that means that our answer must be 500 centimeters. Okay. So let's practice that. How many liters are in 550 milliliters? So I want you to set up the expression in the same way. We're going to start with 550 milliliters, find a factor that takes us from milliliters to liters, and then end up with an answer in liters. See if you can put that together. got some good setups, it looks like. So let me show you how I would set this one up. So I'd start with 550 milliliters. And I want to end with some liters. So that means that we need a factor where we have milliliters in relation to liters. So how many liters are in a milliliter, or how many milliliters are in a meter, or in a liter?
1 liter is 1,000.
Yeah, we go back up to our prefixes here, and we see that just like millimeters or milligrams, there's always 1,000 of the milli unit in the regular unit. So that tells us, and let me rewrite that down here so we can see it. We know there are 1,000 milliliters in 1 liter. So then we can put 1,000 down here and 1 here. 1,000 milliliters in 1 liter. So multiply through everything on top. That's 550 times 1. It's 550. Divide by the bottom, which is 1,000. 550 divided by 1,000 is 0.550. So 0.550 liters. The most difficult part of these types of problems is getting things on the top or the bottom in the right place. Because if you flip it, you put the wrong thing on the top or the bottom, you're going to get the wrong answer. My feeling is that the best way to do that is following the units. Make sure your units cancel. So milliliters cancel with milliliters, top to bottom cancel. And then make sure that the unit is the conversion factor here, the number is with the same unit that it would be in this kind of a writing. The other way to check it is like we talked about there, just thinking about whether or not it makes sense. A milliliter is smaller than a liter. So if we have 500 milliliters, if we would have flipped that one by accident, we would have come up with 500,000 liters. So think about how much is a milliliter, the little bottom of your little graduated cylinder from yesterday, and how much is a liter, like this. So is 500 of these the same as 500,000 of these? Probably that doesn't really make sense. So that's a signal that maybe you got this thing flipped and you've got to turn it back around. The really useful thing about this method is when you start having to convert multiple things, you can do it basically at the same time instead of having to go step by step. So let me show you another problem that looks like that. How many gallons are in 75,000 milliliters of water? Now, gallons are a US or imperial unit. You don't need to know how many gallons are in a milliliter or how many milliliters are in a gallon. Does anybody know offhand? Okay. We can look it up, but you don't need to know these kinds of conversions. But let's say you looked up some conversions, or they were given to you on an exam or something like this, and this is what was given. 946 milliliters is 1 quart. And there are 4 quarts in 1 gallon. So those are the conversion factors that you found, let's say. Notice that there is no factor here that tells you exactly how many milliliters are in a gallon, which is what the question is asking. We've got milliliters to quarts, and we've got quarts to gallons. We don't have milliliters to gallons. So we have to work that out ourselves. And that tells us that this is going to take more than one step. So here's how we do it. You set up a little plan for yourself. what's the path that you're going to take through these units? So we start with milliliters, because that's the number we're given here. Where are we going to go from there? To quarts, because that's the only thing we can get to based on these numbers. We've got milliliters in quarts. We don't have milliliters in anything else. So that means we're going to start with milliliters and go to quarts. Then from quarts, we can use that second conversion factor to go to gallons. So that's kind of our plan. We're going to start with milliliters, then go to quarts, then go to gallons. Everything else works the same as what we just did. So we start with the 75,000 milliliters. We set up a couple factors here. I'm going to move myself a little more room. And we follow the units. Our plan in green says go from milliliters to quarts. So that means our first factor is going to be one that allows us to cancel milliliters and instead have quarts. We cancel milliliters top to bottom and end up with quarts. Then our second factor, we want to be able to cancel quarts and instead, whoops, not have liters, have gallons. So the second step will be to cancel the quarts and end up with gallons. Notice I put all the units up there first to follow the plan, and then we'll put the numbers up later. Because if you put the units up first, it's less likely that you're going to get confused and put one on the bottom or the top in the wrong place. All right, so now we look back up at our conversion factors up here. 946 milliliters in a quart, 4 quarts in a gallon. (946 milliliters in a quart, 4 quarts in a gallon). Pull my calculator. All right, so we multiply through everything on top, divide through everything on the bottom. The way I type that in a simple calculator like this is 75,000 divided by 946, and then divided by 4. 19.8. (19.8 gallons). Can you do that? Maybe. Some of you might notice, if you've done this kind of stuff before, I'm not being very specific about how many decimal places I'm writing down in my answer. We just talked about all this stuff about how important it is to have just the right number of decimal places, and then suddenly we throw that all out the window and just write down whatever. In fact, there are rules for how many decimal places, how many significant figures you're supposed to use in a calculation. But we skip that part in this class. That's not considered something that we need to do in this class. So there's a section of chapter 2 that talks about math with significant figures and how to know how many decimal places to write in your answer. If you're interested and you want to go through that, great. But it won't be something that you are required to do in this class. So you can just pick however many decimal places you want to write down in your answer. Usually a good rule of thumb is about the same number as was in the problem. All right. I'm going to have you try one. Before we do that, take a look at this conversion. 4 quarts in 1 gallon. How many significant figures are in that 4 quarts? It's kind of a trick question because, I mean, obviously there's just one number there, but that's actually has infinite significant figures because it's an exact number. And there were some questions about this on the lab. There are exactly 4 quarts in the gallon, to a gallon. It's not like somewhere between 3 and 5. It's not somewhere between 3.9 and 4.1 or 3.99 and 0.01, it's exactly 4 by a count. So that means that there are exactly a certain number, and therefore that has as many significant figures as you want it to have. Same thing with centimeters in a meter, for instance. There are exactly 100 centimeters in a meter. So that is not a certain number of significant figures, that's just an exact count. But this 946 milliliters in a quart, that has just 3 significant figures. Because if you looked it up, I bet you could find a couple more decimal places out there. I bet it's actually 946 point something 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 milliliters in a quart, because those do not have an exact count between them. So some conversions are exact and some of them are measured, like that one. Okay, and we're going to do an example of that. So let me see if you can work this one out on your own. A patient needs 0.024 grams of, in this case, a sulfa drug. It's a type of antibiotic. How many 8 milligram tablets is that? So you calculate, based on the patient's weight, that it should have 0.024 grams total. But you've got these 8 milligram tablets. So how many tablets should you give the patient? Now you might be able to look at those numbers and kind of just figure it out in your head, and that's great. Write down whatever answer you think of. But also, see if you can put it into a factor label type problem like what we just did above. And see if you can come up with some conversions here to get grams into tablets, a number of tablets. All right, get some stuff set up. So I'm going to set this up like I had the others before I tell you the answer. The only thing that's different about this one is you kind of have to come up with one of your own conversion factors that's not really a standard one based on what's given in the problem. So we know we're starting with grams. And we ultimately want to know how many tablets there are. So in this case, the plan, if we're thinking about our plan of stepping through the units, is going to be from grams to milligrams to tablets. And you might not have thought of it this way, and as long as you came up with something that works, that's fine. Lots of people have different ways of doing these kinds of problems. But I think about it in terms of a plan of how you work through the units, starting with grams, moving to milligrams, and then to tablets, because we know how many grams are in a milligram, or milligrams in a gram, and we know how many milligrams are in a tablet because we're told that here, that each tablet is 8 milligrams. As we've done before, it might be helpful to write down those conversions so we have them. We know that there are 1,000 milligrams in a gram and 8 milligrams in one tablet. So that's one way of thinking about this. Then when we write down our expression, we can use those. So we can say we're starting with 0.024 grams. Then we're going to go from grams to milligrams. And then from milligrams to tablets. Grams cancel, milligrams cancel. Now we just need to fill in the numbers. Between milligrams and grams, there are 1,000 milligrams in 1 gram. Our first factor tells us that. And between tablets and milligrams, our factor tells us there are 8 milligrams in each tablet. So our final unit that is not canceled is going to be tablet or tablets. So if I pull up that calculator again, multiply through on the top, divide by the bottom, 0.024 times 1,000 divided by 8. 3 tablets. Now, some of you may have seen that in a different way. Have thought, okay, 0.024 grams, that's 24 milligrams because milligrams are the first 3 decimal places. And 8 milligrams in 24 divided by 8 is 3. If you did something like that, because you're just used to working with this, that's fine. And that will serve you well most of the time. But sometimes the problems will get complicated enough that you will want to set up this kind of a thing, canceling out your units as you go to make sure that you've accounted for everything. All right. How's that feel so far? Good? Let's pull one of these out of the book, out of the homework, and see how we can do working this out. This is a pretty tricky one. But I'll show you how we can step through it. what is a cholesterol level of 1.85 grams per liter in the standard units of milligrams per deciliter? For whatever reason, somebody came up with this, the standard units for this measurement should be milligrams per deciliter. We didn't even talk about deciliters, but we can look it up. So we'll need to know a couple things for this one. We've got grams and milligrams on the top, and then we've got liters and deciliters on the bottom. This is what we call a compound unit, so this is actually a density, or really a concentration in this case, where we have a unit on top as well as a unit on the bottom. That slash, if you haven't seen that, that means per. So this is another way of writing this would be saying that there are 1.85 grams of something, cholesterol in this case, in 1 liter. That's what that slash means, grams per liter. Another way of saying that is per 1 liter. So when we write that following our units, we have to have a unit on top and a unit on the bottom of the expression, of the fraction. And we want to set something up so that ultimately we have milligrams on top and deciliters on the bottom. So this is a little bit different because now we're converting units on the top and units on the bottom. Let's first look at just the top because that's what we've been doing so far. If it starts with grams and we want to end up with milligrams, what do we do? If we're going to, go ahead.
You multiply by 1,000 milligrams over 1 gram.
Right. Yeah, exactly. So we're going to set up an expression where the gram is on the bottom and the milligram is on the top. That way, grams cancels with grams, and we're left with milligrams. We know from all the stuff we've just been doing, there are 1,000 milligrams in 1 gram. Okay, so if we just stop there and we evaluated this expression, our final unit would be milligrams per liter. So we're close. Instead of grams per liter, we have milligrams per liter. But what we really want is milligrams per deciliter. So to get to that, we need an additional term. How are we going to cancel that liter on the bottom and turn it into deciliters? Anybody have an idea about that? Yeah. Right, yeah, you're both correct. So if we want to cancel something that's on the bottom, we want to put the same thing on the top, and then those two will cancel out because they're opposite. So we'll put the liter up here, and then the deciliter on the bottom. That way, liters will cancel. And this is not one that you need to know in your head, but you might know it anyway. There are 10 deciliters in a liter. A deciliter is 1/10 of a liter. Okay. So we evaluate that out, 1.85 times 1,000, and then divided by 10 tells us that the final answer will be 185 milligrams in 1 deciliter. So 185 milligrams per deciliter. Okay, so that's a good introduction into our next thing, which is density. We're going to be measuring some densities in lab on Wednesday. But anybody know what density is?
It's something inside.
Something inside something? Yeah.
Kind of like not a weight, but
Uh-huh.
some inside that much. I don't know.
I think you're on the right track.
Volume?
It's about volume, something, yeah. How do you know if something is more dense than something else?
More of it in a certain area?
Right, so there's more of it in a certain amount of space. So for instance, I'm just finding random stuff here, but what is more dense? This tape dispenser or this speaker full of air?
Speaker full of air.
Why? Okay,
I'm just
a guess.
guessing because
Okay, that's
they
fine.
talk
Anybody
about
else?
density with weather, so
Okay.
I'm thinking air.
Okay. Anybody else? Yes. That's probably a bad example. I should have brought some extra stuff too. But yeah, it's the amount of stuff inside a given amount of space. I think that's kind of what you were getting at, and then what you finished up with. And that's really the definition of it. Density is the amount of matter in a given amount of space. So let's say you have a cube. If that cube is very heavy, then it's more dense than if that same cube is very light. There's more mass inside. So we can talk about density with respect to things like elements. Things at the bottom like lead and gold and mercury are very dense. Things at the top like hydrogen and carbon and lithium are not as dense, much lighter for the same amount of volume. And the way that we calculate density is by dividing the mass by the volume. So mass divided by volume, or the other way we write that is fraction style, mass over volume. But there's really another way to think of it, and that is as a conversion factor between mass and volume. So we'll often write something like a density in common units for density would be, let's say, grams per 1 milliliter. Mass, grams, divided by volume, milliliters. What is the density of water? Anybody know?
1.
1, yeah. So the density of water is 1 gram per 1 milliliter. Another way that can be written, 1 gram per milliliter, or 1 gram per cubic centimeter. A milliliter is a cubic centimeter. So notice that looks a lot like these conversion factors we've just been dealing with. It's got a unit on top and a unit on the bottom. So if you had the volume of something, if you had milliliters and you wanted to solve for grams, you would use the density for that. If you had the mass, grams, and you wanted to solve for the volume, you would use the density for that as well. Let me show you what density looks like. There's a picture in the book here. Find it. So hopefully you can see that picture. Here's some water in a beaker. And you can see the densities of some different things in that water. So if you look down at the bottom, the lead, density of lead is about 11. So that's, sunk nicely down right at the bottom there. The aluminum, also far more dense than water, so it sinks right down to the bottom. Water is 1. Ice is a little bit less dense than water. There's actually a little bit of space in ice. That's very unusual. Most solids are more dense than their liquid counterpart, but water is different that way. So ice is a little bit less dense. So you'll notice it floats in the water with just the tiniest bit peeking out because it's just a little bit less dense than water. Cork is much less dense than water, so it actually pretty much sits on the top of the water with just a little bit protruding down into the water. because of its very low density. So density affects, because it's the amount of mass in a certain amount of area, it affects how these things interact, how gravity acts on these things together. If you see, if you put oil and water together, they don't mix, right? Which one goes on top? The oil, right? So what does that tell you about the relative densities? Right, oil is less dense than water because oil goes on top. If it were more dense, it would sink to the bottom. That kind of confuses people sometimes because we think of oil as being thick and heavy, but density-wise, it's actually lighter than water for the same amount of volume. There's less mass in there. The thickness and the heaviness comes from its viscosity, or how resistant it is to flowing, which is something different. Okay, let's look at a calculation that involves density and how we might use that. One thing I want to emphasize, it's not different from what we've just been doing. I think that's an important point. There's no, oh, you don't have to say, uh-oh, this is a density problem, this is totally different. It's not different, it's the same. You just cancel the units the way you need to cancel the units, and that's all. Sometimes there's a density in there, sometimes there's not. So let me show you what that looks like. What is the mass of 2.0 teaspoons of a cough syrup with a density of 1.20 grams per milliliter? So cough syrup is going to be heavier than water because of all the sugar content. Interestingly, did you know that that's mostly why cough syrups work? The actual medication inside them is not as important as the fact that they are dense and sugary and kind of coat your throat. And so for a lot of people, actually, something like honey or just a bunch of sugar and water, kind of making a syrup out of that will be just as effective as a commercial cough syrup. You don't actually need the medication in there. Anyway, that's kind of an aside. So we've got this cough syrup, we've got 2 teaspoons of it, and we're given its density as 1.2 grams per milliliter. We need some more information too. We talked about this on Tuesday, but you don't need to remember it necessarily. There are 5 milliliters in 1 teaspoon. All right. Once again, we want to come up with a plan of converting from one unit to the next to the next. And that plan here is going to be, let's see, we'll start, what are we going to start with? The teaspoons, because that's what we're given. So we're going to start with teaspoon. And what can we convert teaspoons to? Milliliters. Yep. And then what do we want to convert the milliliters to? To grams, ultimately, right? Because the question is asking us what is the mass, and mass is something that we measure in grams. So that's our plan. We started with teaspoons, and we're going to end up with a mass. So we set it up exactly the same. 2.0 teaspoons. First step is to do what? Actually, you know what? Just try it first. You guys try it first, and then we'll go through it and see how you can do. See how you do. I'll kind of start it off here, but don't look up if you're still working. See if you can come up with yours. I got something like this. How's that look? Do something similar? So you follow the units and then put your numbers in. 2 times 5 times 1.2, that's 10 times 1.2 would be 12.0. And that's now grams. Always make sure to have your units on the answer there. Main thing to note about this, even though we used the density, we didn't do anything else different. Density was just a way of relating mass and volume, and that's all. Try one more. We need 575 grams of glucose solution. Density is 1.15 grams per milliliter. How many liters is that? So you want 575 grams. The density is given. How many liters do we need? This time I'm not going to start you off. So see if you can find the plan of going from unit to unit and then set up your expression and come up with an answer. So plan I came up with was grams to milliliters to liters. Does that sound good? Okay. That's how I set up my units, so that grams cancel, and then milliliters cancel. So now it's just a matter of filling in the numbers. Now, we know there were 1,000 milliliters per liter. Make sure when you fill in your density, remember that that 1.15 goes with the grams. It's that many grams in 1 milliliter. So this time it's flipped. So we have to make sure that those numbers get flipped too. Again, if we just follow the units and keep those straight, we shouldn't have a problem. One mistake I see people making with density problems is trying to remember whether to divide by the density or to multiply by the density. And you're never going to keep that straight because problems are always a little bit different. So if you follow through the units and you say, okay, which unit do I need on the top and which unit do I need on the bottom, then you can keep it straight. Just make sure that that number always goes with the grams. So we evaluate that. 575. Now the top is all ones, so we don't need to do that. We divide by the bottom, 1.15, and divided by 1,000, and get 0.5. We'll stick with 3 significant digits here, 0.500 liters. Sound good? Okay. So we can try one more with a few minutes we have left here. Pull one out of the book here. This is something like what we're going to be doing in lab next week, so this is a good one just to finish up on. This is not a unit conversion, but a calculation of density. It's a little bit different. What is the density of this solid object that is weighed and submerged in water? So we weigh this object, it's 8.24 grams, and we stick it in the water. How are we going to get a density from that? Yeah, we count the displacement. So the thing, whatever that is, solid object, cork maybe? It's a little heavy for a cork. I don't know. The thing has a certain mass, and it takes up a certain amount of space, its volume. If we have a mass and we have a volume, we can calculate a density by dividing the mass by the volume. So density is mass divided by volume. In this case, the mass is 8.24. The volume is how much space it takes up. So if we have a certain amount of water and we drop this down into the water, that amount of space is reflected in the new level of the water. So the difference between these two numbers not equals, minus. That is the, whoops, that's not right. Sorry. 4.6 ml. That's the amount of space that that object takes up. The water level went up because of the extra space that that object takes up, so that reflects the volume of the object. That means we can calculate that density as 8.24 grams divided by 4.6 ml. You get 1.79. Oops, not ml. And that's now in grams per milliliter. So you divide the mass by the volume, and you end up with the density. We're going to do that in lab on Wednesday to identify some unknown metals. You can calculate the density in this way, and if you make your measurements carefully enough, you'll be able to tell what kind of a metal it is based on those factors. All right, questions about that? So we'll have our first quiz on measurements, unit conversions, density on Thursday, a week from today. Be a good start to the semester. You'll get a little more practice on this stuff in lab on Wednesday. Start working on the homework. If you don't have a book yet, or you're thinking about trying to find a different one online, that's fine. This is super beginning stuff for any, not that it's easy, but like it's stuff that's in the beginning of any book, any chemistry book, anything online. Just look up unit conversions, factor label method, measurements, significant figures. If you have trouble finding stuff, let me know. But even if you don't have a book, you should be able to find plenty of practice materials for this particular topic. And we'll continue on Tuesday. All right, so have a great weekend.